All right, so plan for today. Finished talking about alkyne reactions. In general, we won't spend as much time on mechanisms as we did for alkenes, because the mechanisms are both similar, but they're also just different enough to make it not worth spending a ton of time dissecting at this point.
Okay.
Um, and then we'll start talking about on Thursday, we'll start talking about free radical reactions. And those are the 3 chapters that'll be on the midterm, if I'm remembering correctly. Along with maybe it's a whole chapter in the textbook, but it's basically some practice doing synthesis. Like a chapter, it's all about like, okay, here's the techniques if you need to add carbons. Here's the techniques if you need to remove carbons. But it's all going to be reactions and mechanisms we've already studied. So that one technically is a chapter, but not really. And I saw your question, Riley, about, yeah. That's because I missed this one. We didn't talk about ozonolysis of alkynes yet. Yeah. That was 3 slides later on our slides, so we didn't quite get to it, and I didn't notice when I read this problem. So yes.
And I was like, we have something that's kind of
Yeah, when we can do the first part, it's still good practice because just like we get it as a word problem, it's tricky. So the easiest thing to do is just write it out. So at the very least, it says a terminal alkyne. So we know we've got R, and we treat it with excess NaNH2, and then we're going to react it with 1 iota of propane. So we're going to have something along these lines happening. So after that first step, we're going to get R, still have the alkyne, and then we have 3 carbons we just added. So 1, 2, 3. Now, even without us having gone through ozone, we could make a guess.
that.
Yes. We don't know what R is because it's just a terminal alkyne.
Yeah. And that part got me to is like, we don't really, I just do random. It's right, you're random and so sick. And I was like, good. And she was like, here, and for random one. And I was like, okay.
So the key here is, and again, we'll talk about ozonolysis in more detail about alkynes, but if you just assume that ozonolysis is going to do something similar to what it did with alkenes, it said you only get one type of molecule. So when we split it in half, we only get one molecule as a result. So what does it tell us about that molecule?
It's natural.
So is that enough to figure out what R is?
Yeah. Which one are you playing?
Right. Sorry. We know it's symmetrical because ozonolysis chops stuff in half, right? Or half these pi bonds. So even without us having gone through ozonolysis of alkynes yet, if we just know ozonolysis is going to chop this molecule.
I was confused because I was like, it's three, not like
right. So since we're talking about this problem, we might as well talk about ozonolysis. We won't go through the mechanism of ozonolysis of alkynes. But basically the net result is instead of getting a carbonyl, you get a carboxylic acid. So when we chop this in half, the ozonolysis looks the same. It's O3 followed by DMS. When we chop it in half, all 3 of those carbon-carbon bonds turn to carbon-oxygen bonds. So we turn it into a carboxylic acid. So the part that was, we'll color code this. So that's what we're chopping in.
Yeah.
We're gonna get 1, 2, 3. The rest of this turns into a carboxylic acid. The red side is still gonna be R, and it's still gonna turn into a carboxylic acid. What we know from this line right here is that the red one and the purple one have to be the same. So that means that R is propyl group. So we can work backwards from there. So we must have started with that's our starting point. So obviously I'm not going to grade you on getting the right answer on this one. I think I'll probably just throw the points out of this one. I'll go back in to the quiz and I'll just make problem 1 worth 0 points. So that'll just make the other ones correspondingly worth more. And that's about the extent that we're going to talk about ozonolysis of alkynes. It's really similar, but the mechanism is going to look different because it can't make that ozonide 5-sided ring the same way because it's got to break 3 bonds instead of just 2. So the mechanism's going to look way different. So with that in mind, we'll leave that mechanism alone. And all we're really looking for with this is when you see this and an alkyne, think carboxylic acid. If you see it with an alkene, it's a carbonyl. All right.
So we're starting alkene and then for the.
Oh yeah, I guess we could finish and name these, right? We want to name the 2 alkynes. So this one is then going to look like 1, 2, 3. So our starting material, 1, 2, 3, 4, 5. So 1 pentyne. And 1, 2, 3, 4, 5, 6, 7, 8. So 4 octane. No sister trains to worry about because it's 180 degrees at each of these. So
The intermediate is what all the time, right?
the intermediate's the 4 octane. And our final result, we're going to get 1, 2, 3, 4. We haven't learned naming acids yet, but they look really similar to a lot of other names we've seen. Throw the acid on it. But we'll spend time on it when we get to that chapter after the midterm.
So you won't ask us the names like this on the.
Not the final products. I won't ask you to name anything we haven't covered that before yet. I expect you to know that this is a carboxylic acid, but not how to name it yet.
Okay.
Any more questions on this one? So I won't try Scott's technique. I'm tempted, but I'm guessing because that Swiffer doesn't work that well without something. So I'm guessing it's one of those squirt bottles.
The 95.
Sure.
Yeah, going from Alkynes to all written problems is a bit of a.
It takes a little bit of practice. I wanted to remind us how naming things works.
Yeah.
So this is another one of those series where we're going to start from acetylene. We're going to deprotonate one side of the acetylene, make it nucleophile, and let it react. Then we're going to deprotonate the other side of the nucleophile and let it react. Did I just give you two problems that we haven't covered yet? I did, didn't I? Yeah, that would be why we haven't done the dissolving metal reaction yet. That's on the list for today. So, but at the very least, we can get to the end of part 4. That's why I don't like it when we start on Wednesdays. It throws off my timing for all my lectures. Sorry about that. I didn't mean to do that to you too, obviously.
It's okay, we just tried our best.
Good. All right, so we're going to pull off a proton, let it react with the metal group. So after step 2, we're going to get then we're going to do the same thing, pull off that hydrogen, let it react with an ethyl group. So after step 4, we're going to see
I got here, I mean, I had it written, the other way, so I had like. Yeah,
that's fine. Still, we'd still name it the same way. It's still going to be 2-pentyne, regardless of which way you drew it, right? Now, this last step is particularly nasty to actually do in lab because you have to take liquid ammonia,
oh,
which boils at about minus 40 Celsius. So we have to keep it under 40 Celsius, and it's relatively strong weak base. And the fumes are really nasty. If you've smelled ammonia cleaning spray and thought, man, that feels really like toxic and harsh, that's at like 0.1 to 1 molar. And pure ammonia is going to be more like 15 molar. And then we're going to take that and we're going to dissolve liquids or metallic sodium into it, which you remember what happens when we throw that in water.
oh, is that the one that like.
It lights on fire, balls up, and then explodes sometimes. Yeah. So we have sodium metal. It'll dissolve into ammonia if you put it with an alkyne. And what happens is you break one of the pi bonds, but not both. You get a partial hydrogenation,
Okay,
where you're going to break one of these, but not the other, and you only get the trans product. So, and I'm going to repeat this again when we get to the right slides in a few minutes so that you've heard it twice. But basically, you erase one of these, add a hydrogen up and a hydrogen down.
and that's it.
And that's it. It's just turns out there's very few ways to take an alkyne and hydrogenate it partly and get it to stop at the alkene. We can take it and we can hydrogenate it completely all the way to the alkene. But if you want it to stop in the middle, we have to get really tricky with how we do it. And the way to do it in a way that gives you the trans product is the dissolving metal reaction.
So. We still need to do transit.
So let's look at what this looks like if we draw it out in skeletal structure. So 1, 2, 3. That's this, right? So the hydrogens don't, but it creates this chain where the chain is trans relative to each other by adding the hydrogens. So technically we're adding the hydrogens in an anti-addition. We're adding the hydrogens on opposite sides, which makes the trans product. To use the proper nitpicky terminology. But I think that's only like 2 slides ahead of where we are. I was really close. I should have pushed those last 5 minutes that we ended early on Thursday and would have seen both of those. And then the final product.
Yeah.
Okay. So that's going to be no E. Two pentene. And that came from the 2-pentine. So, and before it was 2-pentine, it was 1-propyne. And then we started with common acetylene or with the iodine ingredient.
Methane.
Not bad. That's 1. 2 carbons. To be ethane, if it was alkane, it's alkyne, so it's kind of
Yeah,
but that's fine.
I'm like so used to saying, so it's just not, it's not.
That's okay because sometimes we pronounce the Y is pronounced irregularly depending on what molecule we're looking at. So you'll get more practice.
Starting with F, Y.
Even-
That's Y and E.
My favorite cooking show host, Alton Brown, who knows his science, is talking about the had a video that we saw over the weekend where he's talking about the different types of potatoes. What type of potato is best for making a baked potato? Because the different levels of starch and the different forms of starch will give you a different texture on your potato when you bake it.
Okay.
And he pronounced amylopectin as amylopectin, like for the whole video, and it bothered me. But I know it's like,
Yeah.
he's from the South. He's not a scientist. He just knows science. So, but it's still like there's irregularities in how we pronounce things because
There's also so many that are pronounced funky.
that are pronounced funky, yeah, and or things that people have learned from reading instead of hearing it.
Like carbonation versus carbonation.
Right, exactly. The difference, for whatever reason, it seemed really weird that this word was like this for me, but preferable versus preferable. I learned it from reading books, so I said preferable because it's preferable. Like it's you prefer it. It's the one you can prefer. And the first time I said it, like I remember my dad going, preferable? Yeah, that's the one.
Yeah. So are you having this one point?
I'll look at what you did. I just probably what I probably won't take off the points for either. I'll look at what you did, and you know that I was very fair when I asked something unreasonable.
Answer.
Oh, okay.
Yeah, that's true. But
Then
I don't remember when because I got to the 2-pentine, and then it was like the NaNH3,
Right.
that like I was like, I don't know. I'm good.
That's, well, let me,
We did.
okay, good. Turns out when it's a multiple choice question, mass spec is not too hard, right? And then because they're all down here, right, in the drop downs. So, and actually this is the same one that was on your lab. Yeah, the same group. Chlorobromo, phenol, and aniline. Aniline is the amine attached to benzene. Without even looking at it too much, that's definitely bromobenzene because you got that isotope effect, and it's the one that is heaviest. There's a 3-to-1 isotope effect. That's definitely chlorobenzene. Then out of these two, you just have to be careful with your molecular weight. They're both going to have some isotope effects that are a little bit bigger than the main group there. See, nitrogen's going to be the one that's a little bit lighter because it weighs 2 less and only gets 1 additional hydrogen, so its mass should be 1 unit lighter. So that's going to be the. So we could just make that one worth the 10 points, since you're both happy with that one.
Both got one of the points on the first one. We did. We got the first one, but not
okay. And that's fine. I'll make sure that it's fair. And obviously, we didn't cover that. Was not. There are.
I think you still both guessed.
I will give you the caveat of I'm not trying to turn my mistake into a learning experience and punishing you for it. But especially when you get to upper division classes, we didn't cover it in class is not usually going to be a good enough answer because they're going to say, well, why didn't you read the textbook or why didn't you read ahead in the slides?
Sure.
But this OChem, it's tricky. And that's not the way that I teach, but that is a common like attitude, especially in upper division classes. You're expected to be a little bit more, I don't want to say proactive, but like self-sufficient.
Yeah.
Go out and find resources to answer it.
What about this? Should we just not do it? No, we should look at the slides.
Yeah, next time, do the parts you know. Try and go take the next step and know that I'm going to be gentle on grading it because I probably didn't mean to do that to you.
Right.
Hopefully it won't be an issue because I'll proofread my slides better for the rest of the quarter. All right, let's go back to the slides then. Like I said, the very next reaction you're about to talk about is hydrogenation. So most of these are going to go the same way. So hydrohalogenation, so adding HBr, you're just going to do that twice. It's the same mechanism. And it is still going to react. But I have slides for each of these, so I won't go out of order. So for a hydrogenation, if it's written the same way we've seen it before, platinum is the catalyst. You just need to make sure that you have 2 moles of hydrogen because there's 2 pi bonds that you can break. And we get really good yields with that. It works just as well as hydrogenating an alkene. But as I mentioned before, you have to get creative when you try to partially hydrogenate to break one of them and not the other. Because if you try and do that by just controlling the stoichiometry, it seems like that should work. Except that what happens, if you remember that the mechanism for hydrogenation is that platinum surface stuck to it, right? What happens if you try and just control it with the stoichiometry is the molecules that stick to the surface react completely, but only half of them stick to the surface. So if you try and do it this way, you're going to get half of your acetylene stays completely unreacted, and half of it gets completely hydrogenated with basically zero partially hydrogenated. Right, so if we wanted to leave it as the alkene, we have to get more creative. In the term that gets used, basically, you can take platinum and make it less reactive. By making what's called a poison catalyst. And a poison catalyst is still a catalyst, it's still a metal, but it's a mixture of metals that's just not as effective. So it can't fully hydrogenate the molecule. It basically works the same way as regular hydrogenation. You get the syn addition, so you get the cis product, but it stops after one pipe gets broken. So the other way that you separate is just called Lindlar's catalyst. I want to say it's like
It's the same thing as poison.
As a poison. Lindlar's catalyst is a poison catalyst. The poison catalyst just being basically we mixed in some other stuff to it to slow it down or make it less effective. Because this is an example of a case where we don't want it to be fully effective. If we want to leave it like this, we need a poison catalyst. I want to say Lindlar's catalyst is like nickel and tungsten mixed together or something like that. There we go. Palladium treated with calcium carbonate. Trace amounts. I'm thinking of what is that one called? That one's gonna come. There's another one that's nickel mixed with tungsten. Sorry, Lindlar's catalyst is palladium treated with calcium carbonate and trace amounts of lead oxide. Basically, you're just gonna slightly coat the palladium. Palladium is also a really common metal to use as a catalyst. I think I mentioned that it's in catalytic converters. Catalytic converters are platinum, palladium, and rhodium. But basically, you sort of put it with this other stuff. Which is actually, we're kind of artificially mimicking what happens to a catalytic converter when it breaks down. When it wears out, catalytic converters stop working because they get sort of this like film of stuff that doesn't completely react and the exhaust system can't get rid of. And one of the reasons why we don't use lead-based gasoline anymore. You may have not been aware of this, but you know the term unleaded gas. It's because literally they used to add lead to gasoline on purpose because it made the engines run smoother. However, when that created lots of problems because then people are breathing in lead smog in the 60s, 70s especially. So they started using catalytic converters in the 80s and removed lead from the gasoline. But that's effectively what you would do is it makes it less affected by sort of depositing some lead oxide on the surface.
The answers.
You tell me.
So with Lindlar's catalyst, basically we break just the one.
Just the one.
Okay. And then you get one product or two products.
Don't.
Like when we use just straight platinum, we get two products, right?
Why would you say that?
Because we split it and then one side is gonna have just.
Let's just do it like that.
Isn't it one hydrogen up, one hydrogen down?
That's the other one. Lindlar's catalyst always makes the cis product.
Okay. So then the other side is always gonna bend down.
Or up, as long as it's the same direction. As long as your hydrogens are pointed the same way on the same side, then you're gonna put the whatever else was attached is gonna be on, wind up being on the same side as well. So we're gonna wind up with something that looks like,
So we can get this, but
with alkenes, remember they're planar. So if you flip it, it's the same molecule.
so we have the two H2. And breaks both fine.
And actually, for convenience sake, I can draw it that way too, so it looks like this one. But this one doesn't have any hindered rotation and it has no stereo center, so it doesn't really matter. You're gonna get the two methyl pentane regardless.
Where was
The double bond was right here, or the triple bond was right there. We broke both of them, added a hydrogen to each side twice. So we wind up with this. Sure. If we left this as one though, like it was originally written, if I was reading this in general, I would assume that that needs to have an hydrogen to do it twice. If you didn't interpret it that way, you would still get this as your product. You would just only get 50% yield because half of it's gonna stay like that. And so usually, if you have part of your reactant is unreacted, we don't usually rewrite it as a product. Okay. We would just leave it as, right, 50% yield if you wanted to be specific.
Right. So when you give it to us, that we would just assume what we have two.
If it's platinum react, yeah, either just assume you have two, or if you could write assuming 1 mole of hydrogen, you could still write it the same product, you could just write 50% yield. Similar to, typically I'll specify it.
And then it is hydrogen.
This is partial hydrogenation.
And it's in the
Yeah, so our partial hydrogenation alkyne, we need Lindlar's catalyst.
But our, like, the way we would know is happening is the H2 being on top of each other, just that. There'd be other things.
There's one more, the one that we started with. The dissolving metal reduction.
So we would just know it by, the H2.
Yeah,
And then something, I'll go.
yeah, so either platinum, if it's complete hydrogenation, it'll be platinum. If it's partial hydrogenation and you're making the cis product, it's Lindlar's catalyst.
You said there was something.
If we do a partial hydrogenation and we want the trans product instead, we have to do that nasty dissolving metal reduction.
PT gives us this. Yeah.
Correct. PT gives you complete hydrogenation.
Single bonds.
So you go all the way
Lindner's gives us
this, correct.
And what was one that gives us?
This one,
So it's not even H on top.
correct. This is a weird one.
And then it's liquid.
And extreme liquid, so we gotta be doing this at dry ice temperatures.
I mean, how would you even do this? Would you do this? Especially at the end of the stage?
So you could do this in a bath. So what you can do when you need to keep something, I wanna say, that, dry ice sublimates at -70 Celsius. And acetone is still a liquid at not -70 Celsius, so just like making an ice bath to keep something at 0 Celsius, you can make dry ice acetone bath. To keep it at -70 Celsius. So you could do you do stuff like that. To keep it at the right temperature. We would wanna keep this, we wanna make sure that it's in a very dry environment. We don't want any water getting in there, getting messing with our sodium at all. So we do things, we'll do a lab. Later this term or maybe early next term, where we have something similar, where we use sodium borohydride, which is really reactive with water, and we use what's called a drying tube. We'll dry all of our glassware in the oven at a time. And then, and if we were really in like an industrial setting, we really cared about our yield, we would actually assemble our glassware in a full size oven.
With us in it?
Not with us in it. But basically you assemble it completely, put it in the oven with all the openings open and heat it up overnight above 100 Celsius. Turn off the oven, let it cool down, move it into the fume hood, still assembled. So that it's now sealed and completely dry on the inside, and then we use a dropping funnel to add our stuff to that entirely closed system.
Okay.
So there are ways to do that, but it basically relies on being really careful. Sometimes you have to do stuff like do it under an inert gas, where basically you don't let any oxygen into the system. You just flood it with either nitrogen or argon. So, but that's getting into the specifics a little bit more. We'll learn some of those lab as we get closer. But yeah, this one is not an easy one. And really because you know, most of the easy applications to think about when it comes to low-chem are medical applications. Very rarely do we actually want trans alkenes. Most living systems synthesize cis alkenes when they make alkenes. Trans alkenes are not really good for the body in most cases. So this is really a niche application. And the nice thing of both about the Lindlar's catalyst and the dissolving metal reductions, we're not going to get into the mechanisms. So we can more or less just remember this is how you do partial hydrogenation and move on. So let's try one. Got a dibromide. We're going to let it react with excess amide. Then we're going to expose it to ethyl chloride. And then we're going to do Lindlar's catalyst. So walk it through each of those steps. And then we'll go over it. step one,
That's
because excess sodium ion, first thing he does is of course elimination reaction, make the alkene. Then of course the second elimination reaction, make the alkyne, and then he protonates the alkyne. So we're showing every intermediate along the way. We make this first. Then we make. I'm gonna draw the alkyne down this way. In the interest of space. This version. Which then gets deprotonated. So when it says excess sodium amide, it means we've got at least 3 equivalents, 3 moles worth. Net result is we get here after step 1. And then we react with ethyl chloride, SN2. Now we're here. Not all day. That's fine. Because we see it's H2 and it's Lindlar's catalyst. We know it's partial hydrogenation. We know it's going to give us the cis product. Feeling okay about that?
Yeah. Then these agents are.
We're going to add 1 to this side and 1 to this side. All right. Here's some other reactions. Actually, let me go back. This slide. These ones really don't change. These ones we can control just by looking at the stoichiometry. So there's really not a whole lot that we need to spend time on when it comes to So hydrohallucination, if we had. If that was an alkene, and we let it react with HBr, we get a Markovnikov addition, right? At the hydrogen here, break the pi bond, put the bromine there. And then it's still an alkene, right?
Yeah.
So we could then do it again. And the mechanism works the same way. So it's really, there's not a whole separate section on these ones because they do everything the same as before. Halogenation. If we had it like this, with a bromine to each side, you break the pi bonds.
So we start with the same. That's what you your pair of kids.
Yeah, starting from the same. I appreciate that you're taking note of non-standard arrows and wondering what they mean, because we pay attention to that. So you can add a total of 4 bromines. 4 chlorines to an alkyne.
What's on top of the second act?
Sorry, more bromine.
The table and this information.
There's the stuff that's simply organized, and there's the stuff that doesn't fit. Yeah. The reaction summaries, I think I pulled them out as PDFs, them on Canvas. So addition reactions and alkynes. I don't have the reaction summaries pulled out on this page. Maybe it's on week 3. With them all labeled and what their terms are. There's some good, I know I threw that on top of an already crowded whiteboard. I'm just showing you that it's there. It's not the worst way to organize your thoughts when it comes to these. It's bifunctional group. Here's an alkene. Here's all the things alkenes can do, and then you can go through and label them as Markovnikov or anti-ether, etc. But basically, there's a reason that organic chemistry textbooks are organized by functional group. It's just because trying to categorize this reactions, the reactions of different functional groups and trying to put them into the same categories as other functional groups doesn't always work. With alkenes and alkynes, we can kind of do it. Even that gets a little messy as we're seeing from chapter 8, from the alkenes, yeah. We've got Rocco. We've got dihydroxylation, we've got ozonolysis, we've got hydrohalogenation. We've got antimicrobial hydrohalogenation. Acid catalyzed hydration, mercury, oxymercuration, hydroboration, hydrogenation, bromination, halohydrogen formation, etc. So
No, I mean like the one I made.
So is there one that we're missing here specifically? True, we didn't really talk about this one though. So we're just
There's some oxymercury.
oxymercuration right here.
I have the, do you have it as a white?
Oh, that's what it is. It's that it has. These are two separate reactions, but both are the same product. But they won't if there's rearrangement. So that's our acid catalyzed hydration. That's our oxymercuration. That's probably why the count is a little different. Yeah, because even down here it says 3, but then there's that acid catalyzed hydration and oxymercuration, demercuration, the same number. So if I was picking a place to study from, or at least like a sheet, like here's my checklist of my study guide for this chapter. If you know all of those reactions, or even just go and like cover up the product and practice going around that and filling in all of those, that wouldn't be a bad place to start. Just repetition and starting to recognize patterns. And with that in mind, let's take our break. So let's come back at 5 after.
So y'all have graduate. Stand on the phone. Oh, no, you look at that. The last part of everything, because he uses the.
Problem. That's right.
No, I'm just confused. Cause it's a new number.
All right, we ready to jump back into it? Sooner we get started, the sooner we finish. Um. So we already talked a little bit about results. We're not gonna go into the difference in mechanism. The major result is that we get two carboxylic acids instead of two carbonyls. So in terms of synthesis, if we want carboxylic acids, that could be really helpful. We could get to an alkene in the right spot, but then turn it into an alkyne and then turn it into a carboxylic acid. That gives us another tool in our toolbox that gets us to a new functional group we haven't seen much of yet. The other big difference is hydration. Hydration reactions we spent a lot of time with, right? We had acid catalyzed hydration, we had oxymercuration, and we had hydroboration. All three of them still apply to alkynes, except that they do a they do a rearrangement step where they end up as carbonyls instead of alcohols. So we're going to talk about that mechanism. In general, acid catalyzed hydration doesn't work as well. It's just slower than with an alkene. We kind of combine acid catalyzed hydration and oxymercuration. So it's basically you have to have acid catalyzed. It's going to look kind of similar to a regular acid catalyzed reaction, except that you also have to have mercury present. So it looks a little bit different. It's not mercury to acetate. It's just a mercury to ion, oftentimes in the format of mercury sulfate. But you still are going to make a similar three-sided ring structure with the mercury that we saw before. It's just that after that, then we do the acid catalyzed hydration to do that ring opening. Right, so once we get that mercurium ion, the next step is water molecule comes in and attaches to the more substituted carbon. So it's still more carbon involved. And then once you do that, we get this intermediate. So our second step here was H2O comes in and attaches there. Let's say draw it this way. And then we do a proton transfer step because we'll then wind up with R. We've seen this before. Once we get a water molecule attached, we just do a proton transfer. Something acts as a base. In this case, probably water acts as a base. Pull hydrogen off to make H3O plus. And then this is a step where this bottom part here is when we actually do have a pretty relatively simple mechanism for getting rid of the mercury. Because we still have the pi bond here. So we just basically, the pi bond pulls the hydrogen off, we do a proton transfer to break the pi bonds. And that puts the hydrogen on the same carbon that has the mercury. Because I grabbed this from two different pages in the textbook.
So if we all of a sudden know what it is.
It was, I didn't even test. So then we get this intermediate that looks like a carbocation. It is a carbocation, but it has a resonance structure where we can donate electron density from the oxygen. So we get this resonance structure, but then it doesn't last very long because what happens is the carbon mercury electrons basically move over and reform a pi bond. And it kicks the mercury off. So it's leaving group leaves. And
That's not what it does there.
it is, I don't know really why they're showing it from this resonance. This is the more stable resonance structure, so I guess that's why they would be showing it from here. But either one of these, you can show the same step. Mercury, carbon mercury electrons move over to the empty valence of the carbocation. And then mercury leaves once again. And we get this weird dual functional group.
About the arrow. Would it still work with the second, with the arrow that's right there? No, the one on the left.
No, so if I was gonna draw from here, I wouldn't draw that. All right, so when we get to this point, that is a hydration reaction. We added a hydrogen to one side of the pi bond, and we added an OH to the other side of the pi bonds. So we added a water molecule, just like we've seen before, at the expense of pi bonds. Excuse me. So once we get there, we're not quite done though. Because the problem is that this molecule, this combined functional group called an enol, we're going to see this a lot when we start getting into more esoteric functional groups. Basically, you just slam the endings of two different functional groups together, and it's a new functional group. So this is an alkene with an alcohol, so it's enol.
Yeah, it is.
Right here.
Yes, it gets added.
You get that it's the same carbon with the mercury. And the thing with these enols is that they're not particularly stable.
All evil or
This, we're forming an enol, which is then going to rearrange to our final product. Yes, still acid catalyzed hydration. The reason we break it up into 2 steps, 3 steps like this, is because this can be isolated on its own. It just continuously is going through an equilibrium reaction where it's switching between this form and a ketone. And so they call that process tautomerization.
this one.
That's the word that they get used when when you can go back and forth between 2 isomers that are really closely linked. So it's basically it's a tautomer is a specific type of isomer. It's a constitutional isomer, but it's one that can be switched back and forth. And I believe that the root there actually comes from a Latin word that gets used in math a lot. A tautology actually gets used in philosophy probably even more than math. A tautology means that you restated something in a different way. So if I wanted to say, like, I have 6 eggs, and you said, no, you have half a dozen eggs. That's a tautology. It's like saying something is true by definition, but said in a different word.
How would we know an acid catalyzed hydration is happening to the RNAs? Like
So it's going to look like we this. So mercury 2 sulfate, bottom. What's on the bottom? Step 3 here. No, so that's just because this is one of those reaction series where it does 2 steps, and then the 3rd step here is that the way we write an acid catalyzed hydration for alkynes. Mercury 2 sulfate, we need acid, so since we have mercury 2 sulfate, we usually use sulfuric acid and then water. So it really does kind of look like a combination of oxymercuration and acid catalyzed, because it's got the mercury in it, but it's also acid catalyzed plus water.
Yeah.
All right, so this tautomerization basically works because the carbonyl form gives the oxygen more electron density. So a carbon-oxygen pi bond is usually more stable than a carbon-carbon pi bond because the oxygen is more electronegative, so you give the oxygen more electrons. And it's just, you do a proton transfer, which makes this resonance stabilized intermediate. So it looks, the first step looks just like our first step in acid catalyzed hydration
We still
for
have,
alkenes.
R is just sort of back to the. I know, but like it disappeared. We can't just go from having R to not having. You must like, where did it go? It disappeared into thin air. This is not how I.
It's true, but since art can be anything, I get lazy with it, because our metal is as good a stand-in as anything else for an art group. But I see your point, so we'll keep using the R.
Oh, it disappeared. The rest of my thing can just disappear. I can stop writing it.
Fair. So keep me honest on that. Keep reminding me when you see that. So proton transfer. So we break the alkene, make a carbocation, just like we've seen before, but because it's a carbocation next to an oxygen with a lone pair, it has this resonance structure that makes it pretty stable. This resonance structure, though, it would be totally stable if we just got rid of this proton on the oxygen. So we just had another proton transfer step. All that you have to do for isomerization is proton transfer step to break the pi bonds. Resonance structure forms the other pi bonds, and then another proton transfer. So we wind up with the alkene as a result. And both of these are equilibrium steps. So anytime you have a ketone, this is actually happening constantly.
The arrow that comes from outside of our big parentheses, it could also go to the other, right? Like, is there resonance of either of those?
It could.
Because like either of those could be happening.
Yeah, if we did that, we would make a different type of molecule called a hemiacetal. So we'll get there when we start talking about ketones more. That actually is a very biologically relevant reaction because do we?
I mean, like we do stuff inside them, but nothing to the outside. It's above.
So usually in a resonance structure like this, it's as an intermediate, right? It's something, one of the resonance structures will then react. So it's not unheard of. It might usually be an arrow coming out of the resonance structure.
We just want to show like crossing over the line. Yeah, that's why I was like, but like we literally just did it in the one before. But then no, we added that. But that could also be like over here. It's not necessarily it. Because that's like a whole thing to their parentheses level.
So we will see this fairly often with resonance structures. This may be the first time that we've seen this written this way. But this will continue to be a thing because these resonance structures, the resonance stabilizes it, but usually it's still an intermediate that's going to then react.
And the one that reacts is typically going to be the one on the right side.
Sample size of 2, so it's kind of, I wouldn't make a generalization yet. But I guess if you're thinking from left to right,
Yeah.
then yeah, sure,
Like,
you can say that
the
is the more,
yeah.
yeah. Okay, sure. All right, so this is why our hydration reactions in with alkynes, after you finish the hydration, you're almost always going to end up with a ketone, which almost always then rearranges itself into a carbonyl. Tautomerization, yep.
So is a ketone the same thing as a carbonyl?
A ketone is one type of a carbonyl.
Okay.
So remember, a ketone means that it's a carbonyl that has a carbon on both sides.
Okay.
If it's a carbonyl that is at the end of a carbon chain, It's an aldehyde. So that's our difference between aldehydes and ketones. It's just where are they on the carbon chain? Seems like a small difference, but it actually has a fairly large impact on how they react. So they get classified as two different functional groups.
So just the double bond with the oxygen, like all ones of is.
Yes, this is a carbonyl. The fact that it's between two carbons makes it a ketone.
Got it.
And even a carboxylic acid has a carbonyl with an OH. So that's not a ketone or an alkyne. That's a carboxylic acid. So turns out there's 6 functional groups. There's more than that, but there's 6 common functional groups that have carbonyl as part of them. The 2 that we're talking about for now, most specifically, are aldehydes.
We knew this all at one point in time.
Yep.
So maybe.
Yep.
Something to be this up.
That should come faster the second time.
You want something that's something. No.
The other side about this, so this is the mechanism if it's acid catalyzed, but it turns out actually basic conditions catalyze this reaction too. It goes in a different order. You start by deprotonating this. So it's still a tautomerization. A base catalyzed. The beginning is the same. And all of these conditions are happening.
Wait, where's the? It's not acid catalyzed, so it must be base catalyzed. It's the step before this state.
So when it was acid catalyzed hydration, this whole thing is under acidic conditions. So we see this version of tautomerization.
Where?
Because you have H3O plus around, and remember we have H2SO4 as part of our reactant.
Okay.
So that first hydration of our Markovnikov hydration of an alkyne is going to be under acidic conditions. But if you think back to the next step, I'm going to clear the R's off here in a second, is what about hydroboration? Can we still do hydroboration with alkynes? And the answer is yes, but we do them under basic conditions. But basic conditions, the whole point of me bringing up basic base catalyzed tautomerization is to show that it's the same net result either way.
Okay, so if you have a base catalyzed hydration, okay, and all.
You still are going to get an enol first, and then it's going to turn itself into a carbonate.
So which part?
Depending on where you put the oxygen. So for this one, our acid catalyzed hydration, we put the oxygen on the more substituted carbon because it was Markovnikov.
Right.
So that means it's the more substituted carbon. That means that your enol has the oxygen on the more substituted carbon, which when it rearranges is usually going to be a ketone because it's the more substituted carbon. If we go the other hydration reaction, hydroboration puts the oxygen on the less substituted carbon because it's anti-metallic. If you put it on the less substituted carbon, then when it does its rearrangement, you get the aldehyde.
And that's what this is just base. It's
Hydroboration is under basic conditions. Right, so because it's anti-Markovnikov, we put the oxygen on the less substituted carbon, which on some conditions means we get an aldehyde
So we still have mark and anti-mark.
with our, with our alkynes. For the same reasons, it's the same logic for all of them, because there's still carbon-carbon pi bonds. When you break one of the carbon-carbon pi bonds, you still wind up with a positive charge. So you're still going to try to put the positive charge on the more substituted carbon. So Markovnikov's rule still holds because it's still a carbon-carbon pi bond we're breaking. So let's try drawing our own mechanism. If it's like under basic conditions, can we draw a mechanism for the tautomerization? So under basic conditions, the first step is not going to be protonate pi bond, because we don't have lots of H pluses floating around. So what is it going to be?
Gonna either take the hydrogen off or splice the double bond.
So if we're under basic conditions, is the hydroxide going, has a negative charge? Is it going to be attracted to the pi bonds? No, it's a nucleophile, not an electrophile, right? So where is the obvious target for a nucleophile? Or at base? Where's the acidic proton? Hydrogen attached to an oxygen is always somewhat acidic.
And then we have the NaOH on bond. Finally,
Yeah, it's the sodium substitute, it's not doing anything. It's just sodium. Is that gonna have a resonance structure?
oxygen, right?
It does.
But the hydrogen,
That wouldn't be a resonance structure then, right? Because resonance structures are only moving electrons. But we could do something like that. And out of these two options, yes, probably more stable because we're gonna have a negative charge. Everything still has full valence either way. We're gonna have a negative charge. Probably makes more sense to put it on an oxygen. But either way, that puts, we have a resonance structure with a negative charge on a carbon. And if we have a proton source around, what could that negative charge do? We have just water molecules.
or
Remember, we're trying to get to this. We're trying to show the steps to get there. So we don't want to go back to a carbon-carbon double bond.
most of the.
Exactly. So the net result of this is it looks a lot like we pulled that hydrogen off and stuck it there. In reality, it's two different hydrogens, but it's not a bad way to think about it. Pull a hydrogen off here and turn it into a double bond. You make up that extra bond within that other hydrogen. So, and just like we've seen, this is not the first time we've seen a reaction that could be either acid catalyzed or base catalyzed. And in most cases, when we have reactions like that, all that's really changing is the order of the steps. In both cases, we needed to deprotonate the oxygen and we needed to add a hydrogen onto the carbon. It's just under basic conditions, deprotonate first and then add the hydrogen. Under acidic conditions, we add the hydrogen and then deprotonate. We're gonna try Scott's technique.
Wait.
Okay. Have you seen Scott when he's in here with the whiteboard? It's he fills the entire whiteboard with.
So he just use like slides.
No, he does. I mean, he does occasionally, but he does most of it just by handwriting everything. I forget things too much for that.
Yeah, me too.
Okay.
That's pretty neat, actually.
It is. Okay, Scott. Yeah.
I wonder how long it's been to come out of that place.
Well, this is now the third year that we've been in this room, so. Yeah, I don't know if they changed something about the formulation of the dry erase pens or something about the way they make dry erase boards, but they don't erase as cleanly as they used to.
It's been a total mess, right? They
Yeah.
just, they smear instead of like erase. Still erase. Yeah. And sometimes you really gotta press into it.
Probably it's because they switched to more sustainable and less toxic components in the markers. I know. And this is why chemists really don't want to give up their easy building blocks for synthesis stuff, right? We know it's better if we went fully sustainable, but it would make things so, I know. Anyway. All right, so here's the actual mechanism as drawn out more cleanly. Deprotonate the oxygen, that makes our, what they call, this is called an enolate ion.
Base calories come from the nickel, like mechanism, we can write down in our note,
Yeah, both tautomerization reactions will happen. So you can kind of put them in there really, it's the same thing either way, it's just proton transfer to the carbon.
So there's acid catalyzed, base catalyzed, and the hydroboration oxidation.
The hydroboration oxidation is a different thing.
Right, those are three different.
And we already studied this one last chapter, the hydroboration. So it's only two new ones and they really get to the same place. It's just you switch the order. So yes, but don't let it intimidate you because they're both short and they're the same steps in reverse order. All right, so let's do some practice with these.
So if we go step by step,
If you could compare some steps like, oh, okay, I know that both of those are working together. I'm gonna deprotonate the acetylene and I'm adding methyl group.
right,
You don't have to do one, then two, you can do after steps 1 and 2, your plan intermediate.
go through the hydrogen from?
So the methyl
Yes, sorry.
is gonna go, yeah, in this case, it's a symmetrical molecule. But it's gonna get added to the end of a carbon chain that has the alkyne. Right, because this only works if it's a terminal alkyne, it's alkyne at the end of a carbon chain. In this case, it's only 2 carbons, so it doesn't make a difference, but
And all the Na and H2 does is proteins.
it's just gonna, yeah,
Yes, that's all it does.
in this case, it's just gonna be protein. If you don't have an alkyne yet, it might be making the alkyne, but in this case, we already have the alkyne. So I'm gonna do this again. I'd say, I tried to go the way that you had said the first time,
Which was the other way.
I misremembered. How about that?
First few times you told us it was this way, so I was starting that way.
That's totally fine.
Where would your arrow go? Back up a step.
Okay.
Come on, Tina, go. Like, just
You
where,
got time.
where would your arrow, like, does it come from the sheet to the mind?
So first step is NH2 with a minus charge
Right,
grabs the hydrogen.
yes.
So then we make, after step 1, we have this. And then you've got, if you've got a CH3 with an iodine, that's a good leaving group. So we do an SN2.
No, steps 3 and 4. Can't verify. Because 4 is already 2 things that are working together.
We can recognize that this is hydroboration. And this the oxidation step of hydroboration. This hydroboration had 2 steps to it, right? Attach the boron and then remove the boron.
Right.
So you can break it up and do, okay, after step 3, here's what it looks like, but it's gonna look like that where you've got a boron attached to something. Step 2 is just boron. Right, step 4.
Right, and it's the boron add the OH and the
OH and the H,
OH.
because it's hydration, right? So after step 2, we have this. So now we have to look, okay, it's hydration, so I'm adding oxygen. Breaking the pi bond, I'm adding oxygen to one side and hydrogen to the other.
What happened to the R to the H?
So with alkynes in particular, we see it written this way because remember that if it was BH3, we had to do the same step 3 times in a row. And it got really repetitive to show the same step 3 times in a row. Basically, this is just another way of saying, okay, if it already has 2 R groups attached, then we can do it in a 1-to-1 stoichiometry. Don't need to show times 3 every time. So this is just another way of saying we're going to do hydroboration. You can see it written as BH3, or you can see it this way, where you just have 1 hydride left.
So that's what we're drawing.
I would have skipped step product from step 3 and gone straight to the product from step 4, because as soon as we recognize that these together are anti-mark hydration. We don't need to show an intermediate after step 3. So anti-mark means we're putting the oxygen on the end. So we're gonna get something that looks like, we're gonna get an enol that looks like this.
And you would put a 4 of the apples.
You don't have to, so
You just.
for this problem, it's what's the final product? We're showing our work just so that we can keep track for practice. If you wouldn't have to write the 4, but yeah, be consistent with what we did before. Yeah, after step 4, we get this. But then that's still not our final product. Because we made an enol. And what do enols do? Yep. Or aldehydes. But it's same way, it's a carbonyl in either case, right? So what's gonna happen is we're gonna pull that hydrogen off and put it over there instead. So that one makes sense. Try the next one. Hg is mercury. The Hg is for the Latin name, hydroargentum. Mm-hmm. Literally means liquid silver. That's the top polymerization, right? So we need another key. anytime you see phenol, should automatically turn it into the carbonyl version, because the carbonyl versions are more stable. So I guess technically, I should show this as an equilibrium error. It is always an equilibrium error. But for most of them, it's like 85 to 15. It's gonna favor the carbonyl form. So in this case, we started from acetylene. And we ended with, if we're the IUPAC name for this, it's a ketone. So the IUPAC name ends in -one instead. So it'd be 2-butanone.
Okay.
But this is another common name that you can buy it at the hardware store. It's a really common paint thinner called methyl ethyl ketone. So it's got a methyl on one side of the ketone and an ethyl on the other side of the ketone. So you can throw this in when you're talking to anybody who's done any work painting or refinishing things. If you throw in MEK as an abbreviation talking about it, then they'll know you're legit. Like the old school people still go over to Nevada to buy MEK. You can't buy it in California, but it's a really good solvent for paint and finishing wood projects. Yeah. And if you go into that hardware store in California and ask if you can buy MEK, you're going to get a bunch of old dudes grumbling about how California is ruining everything. Yeah. Just so you know what you're getting into. That's your idea of a good time, is listening to the old white dudes complain about it, and then go for it.
Why is it so bad?
It's just, it's a mild carcinogen. It's like acetone. It evaporates really easy. Yeah, can't buy the acetone that you buy in California is actually cut with a fair bit of water. Because that limits some of that. But you should have be washing your hands or your gloves should get acetone on them often. Oh, well, non-acetone nail polish remover is more common these days because it's an ester instead of a ketone, and it doesn't evaporate quite as fast, and it's less carcinogenic.
Yeah, but it's not like spray. They're afraid of it. Yeah, acid though.
Yeah. And you might, so government regulations are actually kind of picky. They might not let you buy it in a gallon container to use as a paint stripper, but they will let you buy it in a smaller container to use as nail polish remover. Because so it's sometimes it's just the packaging that's different.
You can say all of that.
Yeah. Exactly. It would be so expensive. It's also taxed higher to make up for the fact that it has negative environmental effects. So part of the money that makes the acetone so expensive to buy goes towards the environmental remediation needed to clean up the fact that we're using acetone still.
Okay.
It's a pretty common thing to do. There's where you kind of set aside the money before and the consumer winds up paying for the cleanup without even knowing it. All right. That's a perfect place to stop for the day. The last slide is just more practice.
Okay.
So we'll start with this on Thursday, and then we'll talk about free radical reactions.
And lab today.
And lab today, let's see what lab today is. Let me stop the recording.